Hello, today we will learn about the classification of signals. Basically, some signal classes are more suitable for certain applications than others. So, we should study about the different signal classes often require for different mathematical tools as well. So, here today we will learn about those classes of signals like continuous time and discrete time signals, analog and digital signals, periodic and aperiodic signals, energy and power signals, also deterministic and probabilistic signals. Now we quickly see what are the differences between these classifications of signals. So first of all, if we will talk about the continuous time and discrete time, so we can say this thing that a signal that is specified for a continuum of values of time t. Like here you can see this figure 6a. This is a continuous time signal. Like we if we take the example, so telephone output is a good example of continuous time signal. That is a phenomena, sound waves that are continuous in nature. And if we talk about the b, here you can see this is the discrete time signal that is specified only at discrete values of t, not the continuous values of time, no, on discrete value of t. So, if we want to show the monthly sales of a corporation, so it is a good example of discrete data or discrete time signals. Most real world examples are continuous, but sometimes we also apply the sampling to make analysis for the discrete time signals. Now, analog and digital signal. So, a signal whose amplitude can take on any value in a continuous range is an analog signal. Previously, we talked about the analog, like this is analog. So, if a signal whose amplitude, these are the amplitudes, no? These are the amplitudes, and amplitude can take any value in the continuous range. Maybe here if it is 1 and here it is 2, so there is 1.1, 1.2, 1.3 and so on. So that signal is analog signal, and a digital signal is one whose amplitude can take only a finite number of values. Finite number of values means only maybe the amplitude can have 5. Okay, so 5 values only. 1, 2, 3, 4, 5. So this signal that is having a finite number of values, remember, amplitude. So it is a digital signal. So a digital signal whose amplitude can make on m values in an array signal of which binary m equal to 2 is a special case. An analog signal can be converted into digital signal through quantization. So there is a process of converting the analog to digital conversion. So this is the example that is given to you about the analog continuous time, digital continuous time. This is analog as well as continuous time. Okay, B. Digital, but continuous time. Time is still, like you can see, range of values is continuous. This is analog but discrete time at a specific how many amplitudes are there, number of amplitudes. And this is digital as well as discrete time, like one value at some specific amplitude at some specific time. Then periodic and aperiodic signal, a signal x of t is said to be periodic if for some positive constant, that is t naught, it is true for all t. Like your function will give you the same output, or it is equivalent if you will add a t naught in all of those. Like here you can see this is a periodic signal. Like here again, after a certain time period t naught, it will repeat its pattern, it will again look like just the previous one. Now energy and power signal. A signal with finite energy, remember energy is finite, is energy signal, and a signal with finite and a non-zero power is a power signal. Power is non-zero, but it is also finite, remember. So then it will be a power signal. And all practical signals have finite energies, remember, and are therefore energy signal. Now, causal and non-causal signals. A signal that does not start before t equal to 0 is causal signal. Okay. In other words, x of t is a causal signal if x of t equal to 0 and t is less than 0. Okay. So a signal that starts before t equal to 0 is a non-causal signal. So this is the main difference, that a non-causal signal will start before t equal to 0. Like here, let's suppose here 0 t. Okay. So the non-causal signal can start from here. Okay, like that. Deterministic and random signal. A signal whose physical description is known completely in either a mathematical form or graphical form is deterministic. So what are the possibilities? Either in mathematical form you are able to describe your signal, or in the graphical form you are able to describe your signal. So it is a deterministic. Whereas a signal whose values cannot be predicted precisely but are known only in terms of probabilities or randoms. Very easy. Now this is the example where we need to write a mathematical description of a signal. This signal is delayed by 2 seconds. Okay, and we are going to sketch the delayed signal. So if we see the solution, so very simple. In order to find the mathematical expression of the signal, we need 2 points, point 0 0 and point 1. Okay, like starting from here, no? So it's point 0 and 0. And what the other point, like if we talk about the x-axis, so on the x-axis it is 1, and on the y-axis it is 2. So 1 and 2. So these are the 2 points from which the signal passing. Now here, if we denote x minus x naught, so x1 minus x naught, what is x1? That is 2. What is x naught? That is 0. Then what is the time t1 here? T1. What is the time t naught here? From where it is starting. So simply by putting in the formula, we will get x minus x naught, that is 0. We know this thing. Then x1, that is 2, minus x naught, that is 0, divided by 1 minus 0, that is t1 minus t naught, and t minus t naught, that is here in our case t minus 0. So if we solve here, the left hand side here we have x, that is equal to, here if we solve, t2. So we can say this thing, that x of t, mathematically how you will describe, is having 2t when time is greater than or equal to 0 and less than or equal to 1, because this is given to you. Okay, these 2 points were given to you. So you are describing this signal. So it is the range of the time is 0 to 1. And what was function? 2t. All other, if you observe, here also it is 0, here also it is 0. So it is 0 elsewhere. So this is just the mathematical description of the signal that is shown to you in the sketch. This is sketch. This is mathematical expression. Yes. So this is another, like if we apply the same, okay, mathematical description, but we want to apply the delay by 2. So very easy, just replace the t. What was the expression, mathematical expression? We say this thing, x of t is equal to 2t when time is greater than or equal to 0 and less than or equal to 1, and all elsewhere all it is 0. Now if you want to delay it by 2, so we have to subtract 2 from this as well as from this. So how we will solve it? Like 2 t minus 2, delay by 2. And here also we have 0 is less than or equal to t is less than 1. So instead of t, we will have t minus 2 because we want to apply by. And we can write them separately. So we can say this thing, and 0 is less than or equal to t minus 2. So what we will have, if we move the t over there, so minus t is less than or equal to minus 2. It's mean t is less than or equal to 2. Okay, one range we get, t is less than or equal to 2. Now see the other part. The other part is this one. This one. Now we solve this. T minus 2 less than 1. So it's mean if t is there and 2 moves over there, so it will become 1 plus 2, and t is less than 3. So we can easily combine these two ranges. So we can say this thing that t is less than 3, but because it was negative, negative cancel out, so we are going to get that t is at least greater than or equal to 2. So 2 is having the greater, because it was, if we talk about this part, like this part, and we want to move the 2 over there, so what it will have to, so it's mean 2 is less than, 1 minute, I do it quickly again, this 2, we are right now solving this part, this 2 is moving here, so it will become positive and this is less than or equal to t. So we can write in this way here. So and then obviously sketch will also be from 2 to 3 and 0 also as well. After that, some signal, useful signal models. If we talk about the model, so basically these functions play very important role: step function, impulse function, and exponential function. Not only do these serve as a basis of representing other signals, but their use can simplify many aspects of the signals and systems. Simply, if we talk about the useful signal model unit step function, that is U of t. So, causal signals can be conveniently described in terms of unit step function, and this function is defined by, this thing that causal signals start after 0, okay, or at 0 here. So, they can be described easily with unit function. So if you see this particular case, so here when time is greater than 0, unit function is 1, and when time is less than 0, unit function was 0, signal was 0. So the unit function is useful in representing other signals. For example, the rectangular pulse depicted below A can be expressed as the sum of two delayed unit step functions. So yes, if there are two delayed unit step functions and we want to take the sum of those, so we will be able to get the rectangular pulse. So if let's suppose u of t delayed by t second, we can represent it. And here, this is the example, the unit step function to describe the following signal, and you can see its a solution that basically we are having the sum of two signals, and that are here two components, xt is having two components, and then the another model is the unit impulse function that we denoted by delta t. So is one of the most important function in the study of signal system. This function was first defined in two parts, like here you can see, when time is not equal to 0, it is 0. So we can say this thing from minus infinity to plus infinity. If we have it is equal to 1, its derivation, integral part, integration is 1. We can visualize the impulse as a tall, narrow rectangular pulse of the unit area like this. The unit impulse function, multiplication of a function by impulse. So it will become the unit impulse. A multiplication of a function by an impulse. So since the impulse has non-zero value, only at t equal to 0 and the value of phi of t at t equal to 0 is phi of 0. So we can obtain this thing that phi of 0 and delta t when there is phi of t and delta t equal to 0. So this is just the multiplication of continuous time function. This is the continuous time function. With an unit impulse located at t equal to 0 results in an impulse which is located at t equal to 0 and has a strength phi 0. So this is just the generalization and useful again signal model, that is the unit impulse function. Sampling property of unit impulse function is described over here, that you can follow provided phi of t is continuous at t capital T. So, okay, this result means that the area under the product of a function with an impulse phi t minus t delta t minus capital T is equal to the value of that function at the instant at which the unit impulse is located. This property is very important and useful as known as sampling or shifting property of the unit impulse. So here you can see the derivative of the step function does not exist in generalized sense, and it is in fact delta t. Exponential function that we represent e raised to the power st. This here the s is a complex in general. So you know this thing, s has imaginary part and real part. So we can write in this way, if we replace this s with the imaginary part, we can write in jw form, no? Then theta plus jw. And you know, if e raised to the power theta plus jw t, so we can write this e raised to the power theta t plus t jw. It's mean e raised to the power theta t times e raised to the power t jw. Okay. And if we further solve, in order to further solve, we know this thing e raised to the power jw omega t is equal to cos omega t plus j sine omega t. We know this thing from the first video if you see about the complex numbers. So we can write here, instead of this, we can write the equality. Since the conjugate of S star, so S star, that is the conjugate of S means instead of here plus, we will have here a minus conjugate. And if we solve again, so we will have here also minus. Other thing with the same. So conjugate is just having you here minus. And you can solve. So what you will get, the adding two components, conjugate as well as the additional. So you will get the exponential function. Further details are here. So we will see in the next